So we're going to talk about today what's the impact of storing inventory in multiple locations versus aggregating it and storing it in a single central location. And so I think one of the best ways to think about that is to think about this through an example. So let's consider that a company operates 3 regional distribution centers which need to fulfill demand. And so to give you some orientation of this graphic, first, the dots are demand points and the squares are distribution centers, or DCs. And so in this example, we have 3 separate distribution centers. The first, the blue one, fulfills demand for all the blue dots. The orange one fulfills all the demand for the orange dots, and the green distribution center fulfills the demand for all the green dots. And so what we're interested in here is thinking about our inventory and how much do we have in this network. And so to be able to figure that out in terms of safety stock, we need to understand our lead time. So remember, our lead time is the time from when we place an order to when it shows up. And in this example, the lead time to any of these distribution centers is 4 weeks. And so what is an application of that? Would be somewhere when your supplier is overseas and they send a shipment, oftentimes a container worth of goods via water, and it goes through a port and then gets sent to any distribution in the US would take 4 weeks. And so the lead time from the supplier to any of these is 4 weeks. And then if we look at the demand, so we know the weekly demand in each region, which is normally distributed with a mean of 1,000 and a standard deviation of 300. So that means in region 1, we have weekly demand on average 1,000, but there's variability, and so the standard deviation is 300 per week. Similarly for region 2, and similarly for region 3. The other thing we know is that the demand in each region is independent. And so what that means is the demand in region 1 is not influenced by what's happening in region 3 or region 2. And so they're independent of each other. So if we want a desired cycle service level of 95%, how much safety stock is stored at each of the regional distribution centers? And then how much safety stock is stored in the entire network? And so that means the safety stock at region 1 plus the safety stock at region 2 plus the safety stock at region 3. And you can notice here that I've simplified a little bit this graphic. The reason is we are interested in the safety stock at each of these distribution centers. And then those distribution centers use that inventory to fulfill their demand. And so another thing to note is if I look at region 1 or region 2 or region 3, because they're independent and they each store their own inventory, we can study region 1 by itself, and then study region 2 by itself, and then study region 3 by itself, and sum them together. So let's start by looking at region 1. So if we ask ourselves this question, we want a desired cycle service level of 95%. How much safety stock is then stored in region 1? So this is actually something we did in the previous lectures. This is just using the safety stock equation. And so as a reminder, what influences safety stock? Well, it matters what the cycle service level is. It also matters how variable your demand during lead time is. And so we need to calculate the standard deviation of demand during lead time. And we weren't given that. We were given that we have weekly standard deviation of 300 units, but we aren't given directly the lead time standard deviation. And so we need to calculate that. And so as a reminder, we are given the per period, but we need to get the standard deviation of lead time demand. And if our demand is normally distributed, then we get to calculate safety stock using this equation. And so in this example, we are normally distributed, so we get to use the Z value. And the beauty of that is we don't have to play around with calculating tediously the cumulative distribution function. So we get to use Z instead of using the cumulative distribution function, but we still need the standard deviation of lead time demand. All right, so let's use this equation. So again, what were we given? Well, we were given that the cycle service level was 95%. So we can go look up 95% on either a Z table or use norm.inverse. in Excel. And if we did that, we'd get that Z is 1.65. And so we also need to figure out the standard deviation lead time demand. We know that the lead time is 4 weeks exactly. And we know the per period, or the per week in this case, is standard deviation, which is 300 units. So we can now plug that in to this equation. And if we do so, we get that at region 1, we have 990 units of safety stock. So at region 1, if region 1 has its own inventory and only fulfills the demand that is in region 1, it will need 990 units of safety stock. So now we can think about, well, we need to know not just region 1, we need to know region 2 and region 3, and then we want to understand the whole network. One thing to note is if you look at region 1, we just calculated that region 1 has 990 units. But one thing you could think about is that we could redo this. We could do this again for region 2, but it has exactly the same data. So we could do the same thing over. We'd get that that had 990 units, and similarly for region 3. So each one has 990 units of safety stock. And remember, safety stock is there to buffer against variability in demand. And because we have a quite long lead time, 4 weeks, and quite high demand and standard deviation of weekly demand, we need 990 units to have a cycle service level of 95% if each region holds their own inventory and operate independently. So over the whole network, if we sum all of that together, that means we need 2,970 units of safety stock across the entire network. If we have a decentralized inventory policy, meaning each of the regions hold their own inventory and operate decentralized, meaning they operate all by themselves. All right, so in terms of what did we just do? We use this equation, okay? So if you want to calculate the total safety stock in a decentralized option, that means we store inventory in each of the K locations, and those K locations operate independently. What we just did is we used this equation. And so what did we do? Well, we calculated for each one of the K regions. In our case, we had 3, K was 3, is we calculated the Z value because it was normally distributed using the cycle service level. We used the square root of 4 because our lead time was 4. And then we had the per period, the weekly standard deviation, and did that. And so we did that for each of them, and then we summed them up for all 3 different locations. And that gives us the total safety stock and a decentralized option. But what if, instead of storing our inventory in these 3 separate regional distribution centers, what if a company said, no, I just want a single central or national distribution center? How would that influence our inventory? So I want to ask you, do you think our inventory of specifically our safety stock, do you think it would go up? Do you think it would stay the same? Do you think it would go down? All right, we will get to the answer to that question, but see if you have any intuition, okay? So what do I mean by that? Instead of having 3 separate ones, I have one kind of larger distribution center, and then all of these different regions are fulfilled by that central distribution center. Okay? And so here you can note that there aren't 3 separate locations, there's 1, but all the demand gets fulfilled from that. And we still have a lead time of 4 weeks in this example. So again, this distribution center is located somewhere in the US, and so the lead time from the supplier is still 4 weeks. All right, so how do we get at that? So how does aggregation or centralizing inventory from 3 locations into 1 affect our mean and standard deviation of lead time demand? So we have to be given some information. So we need to know the mean per period demand in each of the regions. We also need to know the standard deviation per period demand in each of the regions. And then we should know the correlation between demand in each of these regions. So in our case, we've assumed they're independent. That means the correlation or rho is 0. However, that isn't always the case. And so if your regional demand is correlated, you need to know what the value is for that correlation between each of the regions. So once you have that, we can use this equation to calculate the centralized demand per period. And so what are we trying to calculate here? We need the mean. So what does that mean? It means if we have all of these different regions, on average, how much do I get per week if I don't consider each of them independently, but I sum them together? And like lots of things we'll talk about in this class with inventory, expected values do exactly what we want. So if you think on average, region 1 has so much per week, and on average, region 2 has so much per week, and region 3, you can just sum that up, and that would be on average how much the whole network would be demanding per period. The variance or the standard deviation is a little more complicated. And so we can't sum standard deviation, so it's incorrect to just sum up over all of the different regions to get the standard deviation. Instead, we need to work in the variance space, and so we need to sum variances and use this equation. And one thing to note is if the region's demand is not independent, if they're correlated, we need to consider this rho factor. However, if they're independent, this goes away because rho is 0. And so we do need to play in the variance space, and then remember the relationship between variance and standard deviation is we can always get the standard deviation by taking the square root of the variance. And so this equation here gives me the standard deviation of centralized or aggregate inventory per period. One thing to note is if in a special case, so the previous example is kind of a general equation, if you have the special case where it's IID, so IID means it's independent and identically distributed. That means you have to have independent regions, but you also have to have the demand from each region is the same distribution and has the same parameters. So in our case, we did have IID. That's because they are all independent regions. Region 1 is independent from region 2 and region 3. And they're all normally distributed, and they all have the same mean and standard deviation. So if you have that case, you have IID. And the beauty of IID is there's a nice, easier equation to get the standard deviation of centralized demand per period, which is this equation here, which is the square root of K times the per period per region standard deviation. And so that's the impact on the lead time, mean, and standard deviation. What's the impact on centralizing or aggregating demand into a central location on safety stock? And so the key here is this first equation is what I showed you before, what we did when we had 3 separate distribution centers. And the second one is the one we need to use if we centralize them. And one thing to note is that the main difference here in these 2 equations are only in these things I just highlighted. So first of all, the standard deviation of centralized demand has changed. And also the summing here over K is what happens in the decentralized option. You notice there's no sum over K in the centralized system. And so where does the K come from? It gets hidden inside the standard deviation of lead time, or of per period centralized demand. And so if I go and remember from the previous slide, this equation, or this sigma here, how did we calculate it? Well, we calculated it in general either using this, but let's look at this equation in the simplified one. What we're doing, instead of summing over K in the decentralized one, we're using the square root of K in the centralized one. And so the square root of K is always going to be smaller than the sum of K. And so the short answer to, do you think we will have more or less inventory if we go from 3 locations to 1 location? The answer is we will have less safety stock as long as the demand is not perfectly correlated. And so we will always have less or equal to the amount of safety stock if we centralize versus decentralized, and mathematically these equations show that. All right, so you may say, okay, there's all these equations, let's get back to the example. Okay, so if we go back to this example, and instead of having 3 separate, we have a single distribution center. And remember, each of these regions is assumed to be independent, and we're also going to assume that the demand didn't change just because we changed our supply chain configuration. So in other words, our demand is independent of how many distribution centers we have and where they're located. The other thing to note is that region 1 has a weekly demand that's normally distributed with a mean of 1,000 and a standard deviation of 300. Region 2 also has that same distribution. It's also normally distributed with the same mean and standard deviation, and so is region 3. And so what that means is, first of all, because it's independent, rho is 0, and because these are the same, they have the same normally distributed with the same mean and standard deviation, we can say each region is IID, independent and identically distributed. So for our example, we can use that square root rule equation because they're IID. That won't always be the case. You will get a chance in a homework problem to do some stuff using the IID, but not all of the homework will do that. And I'll do another video to explain how to do those. All right, so how do we calculate that? We need to calculate the safety stock in this centralized one single distribution center case. So we can use this special equation because we have IID. Among regions. And so what do we need? We need to calculate this. And so as a reminder, we have a weekly demand in each of these regions that's normally distributed with a mean of 1,000 and a standard deviation of 300. So let's plug that in, okay? And so if we use that equation to get the standard deviation of aggregate weekly demand, we have square root of 3 because we have 3 locations, K is 3. And per period, in this case, per week, we each have that they have a standard deviation of 300. And so the standard deviation of aggregate weekly demand is 519.6. So what does that mean? That's the standard deviation if we pooled all 3 of these regions' demand in one location, and that's per week. That's great. But remember, we need lead time standard deviation. So we need to now use that and then use these previous equations that we've done from before in the other videos. And so as a reminder, lead time from the supplier is 4 weeks. And so we need to use the standard deviation of aggregate lead time demand. We need to calculate the square root of L times the centralized per week value. And so here what we're doing is we're taking the weekly demand and we're just converting it now to a lead time of 4 weeks. And so now we have the standard deviation of aggregate or centralized inventories lead time demand. And we're still not there yet because we're trying to calculate safety stock. And as a reminder, safety stock is this equation. And so we need to use this cycle service level, which we want at 95%. And because it's normally distributed here, we can use norm inverse. If it wasn't normally distributed, we could use a cumulative distribution function. And then we need the lead time here. And so we get that there is 17,000 or 1,714 units if we centralize our demand into one location instead of having 3 locations. So let's compare, okay? Let's compare the trade-offs of physical centralization. And so if we think about this decentralized case, which in this case was the one where we had 3 separate facilities, each of those facilities fulfilled demand in their regions independently of each other. And if we compare that then to the centralized case where we have only a single distribution center, we have one distribution center and it pools or aggregates all the demand from all 3 regions into a single location. So what are the trade-offs there? The first trade-off, which we just showed mathematically, is that the safety stock will drastically reduce in the centralized version versus the decentralized. For this example, we went down from almost 3,000 to closer to 1,700 units in safety stock, and that's significant. And so if your inventory has high cost, that this really makes sense to reduce safety stock and holding costs. You can centralize inventory and reduce a lot of your inventory. So that's great. However, that's not the full story, right? So we have to think of other things. So when you think about supply chain decisions, we really need to think systematically. And so safety stock in the network will always either decrease or be the same if you go to a centralized system. And so that's good. That's awesome. We have less inventory costs, less holding costs. However, that's not the full story. The transportation costs are actually higher in the centralized system. And we can see that by just looking here. Just looking up here, is you can see these blue lines are longer than these blue lines. These orange lines are longer than these orange lines. And these green lines are bigger than these green lines. So the transportation cost of demand has increased because we are further away from our customers, and therefore we need to pay higher transportation costs. This is a big deal also in today's world where we all want our stuff fast and 2-day delivery, 1-day delivery. And that can get really expensive if you need to use different modes of transportation. And so the centralized system will have lower inventory costs, but will have higher transportation costs. And then also in terms of facility costs, the decentralized system has 3 facilities they need to operate, whereas the centralized one has a single one. It might be bigger, but it still has less cost, because when you think about 1 bigger facility versus 3 smaller facilities, there's usually a lot of fixed costs associated with operating a facility. You can think about there's 3 roofs versus 1 roof. There are 3 managers versus 1 manager. There are 3 welcome people versus 1, right? And so there's a lot of setup costs that regardless of how much stuff is going on, you need. And so the facility costs are higher in the decentralized system than the centralized system. We still have not answered the question, should I go decentralized or should I go centralized? And we will explore that in another video. However, one thing to take away in terms of inventory, we're better off in the centralized system than the decentralized one. And so the main key takeaway here is that the average demand faced by the centralized distribution center is equal to the sum of the average demand faced by each of the regional distribution centers in the decentralized system. So if we cared about average, these are equivalent systems. On average, they're equivalent. However, in variability and uncertainty, they are not equivalent. And so here's another example of how variability is different. And so specifically, the variability faced by the centralized system is much smaller than the variability faced by the decentralized system. And why is that? You can think about it in variability terms. If region 1 and region 2, if region 1 this week had a higher than usual demand and region 2 had a lower than usual demand, they cancel each other out. And so that is why the variability, when you pool different points, you get to benefit from the fact that sometimes one will be up and sometimes one will be lower, and they cancel each other out. If they're decentralized, you don't get that advantage. And so that's really where this is coming from. This does matter if demand is independent, or at least when demand is not perfectly correlated. Because if demand is perfectly correlated, what that means is if this one goes up, that one goes up, and you don't ever get that opportunity to cancel each other